one of you make sure he knows what we did so he'll be able to catch up with it. I think he jumped in the room right now. Let's see. Yeah, he made it in. We were waiting for you, Joseph. We saw you fall out of the room and come back again. Okay, so here's the deal. When we take the exam, it's really hard, since I can't see you, I can't monitor you while you're taking the exam, to ensure that there's no cheating going on. And so rather than worry about that too much, we're going to put you on your honor to not cheat. Now, that doesn't mean everybody will not, but it means you should not aid and abet them if they do. The exam also is not conducive to cheating because each one of you will get your own customized exam. The questions are different. Now, not 100% different. There's some that overlap, and they certainly cover the same material. And they've all been tested with other classes to ensure that each question has equal difficulty with all the other questions. So if one of your questions asks you to compute the power, of some amount of current with a voltage drop across a resistor, somebody else may get a similar question with just different numbers. Or they may get one where one of the unknowns is a different unknown. But the testing of it is basically going to tell us that it's, roughly the same difficulty. There is no plan to curve the grades. This summer I didn't need to because everybody either did well enough or it was obvious they were cheating, in which case they failed. So we want to make sure we understand a procedure for doing this. Now, this is a little bit complex, but you guys are supposed to be computer guys, gals, whatever, and so you should be able to follow the procedures to get this done. I did mention earlier that in my other class, I had one student that still at this point has not been able to turn in a successful test. We're going to basically fake a test tonight. It has 2 questions on it, and one of the questions is basically the answer to your homework. So I'll be able to at least review that and see how you did on that. Again, I'm not worried about you getting it 100% right. I'm more interested now in that you get the procedure correct. So here's the way this kind of works. I have a list of names. Your name should be among the ones on this list, and then down near the bottom we begin the other class. So what you need to do is you need to find your name on this list, and you need to copy down the name next to it. So for example, Robert's test in this case would be capital P _1 _11.txt. So copy the number down that's next to whatever your name is here. And everybody should have one, and everybody should have a unique number. If you were to accidentally do the wrong test, you will receive a 0 on it. So it's up to you to make sure that you download the correct one and that you follow the procedure for turning it back in. And it has to be turned in on time. Now, there may be people in this class that have accessibility issues and may have been given extended time by the school. In that case, you'll normally simply just double the time or time and a half the time that I give the class, and you'll simply turn it in late. And that'll already be accounted for as long as I have one of the forms that say you have an accommodation. If I don't have a form that'd be late, again, I don't allow it to be very late because at that point you could be just copying somebody's answers. And so you'd lose a great amount of points for turning in one, even 30 seconds late. So we'll make sure that everybody understands what their numbers is and how we're going to use these. Now, the idea is you're going to take and download a particular text file. The text file is located either on the website, on Blackboard, or some other place that I might tell you to go and find it. It's not necessarily going to be in a predictable place, and this name may not always be as pretty as that. It may be a little more conducive to the grading side of things as opposed to the, making it easy for you to find it. Now, let's assume I was Robert. Robert's my guy that doesn't stick around for class all the time, best I can tell, because his mouse doesn't move enough. So we'll pick on him tonight. He is going to download this file from a particular spot. He will look at this file He will answer all the questions, and then on this same thing that he downloaded, he will enter all of his answers. He'll then resubmit this file to me, and it must be a .text file, and it must be in exactly the format that you received initially. I don't want a file that's a Word document. I don't want a file that is an image of something. I don't want a zip file. I don't want something that is, fancy formatting or something like that. I want a raw text file which has exactly the same name as what you're going to be downloading here. Many times I will have you email it to me, and that's what we're going to use tonight, is once we get this, once you've answered the questions, you're going to email it to me. Then I'll be able to get my guys to check it tomorrow to make sure that you actually follow the directions correctly. Now you might wonder, where the heck am I going to get this? Well, I would have to tell you for any given test. It's not predictable, so you can't go 3 days in advance and find this file, nor can you be guaranteed that your number is going to be the same between exams. You might be 11 on this exam and be 35 on the next exam. So you want to pay a very close attention to the list I give you to make sure you understand what particular one you're going to be using. Okay, I'm going to pretend that I am, Kevin Green. So I'm just going to pretend that's who I am. Now I'm not, neither are you. So you're not going to download this file. So what I'm going to do, at least for this particular exam, is I'm going to go to the website. Everybody go there right now. Once you've gotten there, give me a green light saying you've gotten to the website. Okay, there's still a couple of you that haven't gotten there, or else you're hiding out somewhere. See, those of you that are depending on watching the videos later miss out on all the participation points during class. So you come, you turn it on, you leave it run the whole session. Then at the end of the evening, I have to shut you down because you're not there to shut it down. I obviously know what's going on. And so what you need to do is you need to make sure that you're here so you can participate. Every time I ask a question, there's a participation point available. If I ask you specifically, you're getting a very good mark for participating, a separate mark for did you get it right. So if I ask a question and I specifically address it to you and you don't answer at all, something's up, right? So you want to make sure you're not depending on looking at all this stuff later and trying to work your way through it. I expect you in the middle of class to know what we did during the first part of class. So it's not something, oh yeah, I can just do that later this week. You also will get behind because you won't continue to do it. I have history that says that's the case. Okay, so now what we're going to do, everybody has found this. If you're on a Windows machine, you're going to need to make sure the following is true. I need you to, let's see, is that one here? I need you to open up a file explorer. I got one here that I can open.
Professor, are you trying to share your screen of what you're doing?
No.
Oh, okay.
Not yet. You should be seeing the website and the list of names right now. Is that what you're seeing?
Yeah, that's what I'm saying.
Okay, good. I have a specific file I need to point to here. Okay, this will do. There we go. What I want you to do is in your Windows Explorer here for the File Explorer, I want you to go to the View tab. Make sure in the View tab that the box called File Name Extensions is checked. If it's not checked, at least for the duration of this class, and if you take data structures in the spring with me, make sure that box is checked. That will prevent it from giving you a name that doesn't say .txt on the end of it. I've had people turn in files that said file.txt.zip. So clearly they didn't know they'd created a zip file because what they saw was name.txt. We need to make sure it really is only the name.txt, whatever this is. So p_1_21.txt, for example. So by checking this box, you see the complete name if you're in Windows. If you're on Macs, you have to deal with however you need to know what file types are. And if you're on Linux, it'll probably be correct anyway. So once you've made that correction or fix, or you've verified that it was correct, then what you're going to do is you're going to go to the website. Up in the bar, after the URL that's there, type a /, capital P, a 1, another slash, and then the name of the file that you have, whatever your file name is. Remember, I'm pretending to be somebody else. So whatever the name is, after that, so if I pull this up, you stick this in a notepad here. You would enter a name that looks like this. Remember, your number is going to be different. Now, once you've done that, you're going to hit enter. One of two things is going to happen. It's going to download, and a little download box will pop up down here, in which case you're going to go there when I say let's go to the file, and you're going to grab it and move it somewhere else. Or you may wind up with it opening up inside of your web browser. If it's in the web browser, you can't edit it here. So what you're going to have to do is right-click on it, say Save As, navigate wherever you want it to be saved, and verify that the name is actually whatever we had on this sheet of paper over here. So mine's p_1_28.txt. Notice the first P is capitalized. Also, if it gives you the option, make sure it says it's being saved as a text document. I'm going to save that on my desktop. Now, if you had it come as like this when you originally opened it, what I would suggest you do is click the little arrow there and say Show in Folder. Go to where it shows it in the folder, copy it, and move it to your desktop. Now, if you did what I asked you to do, you'll wind up in an editor that you may not have the same editor I have, but you'll wind up with your test inside of a thing that can edit text files. Now, remember, you can't edit this with Word. You can't edit this with any other tool other than just a regular plain text editor that edits in ASCII. If the file is correct, on the top will be the name of the file minus the .text. So you'll want to verify that the number up here actually is a 28. Let me actually open this in a different editor so it's easier for you to see. So this number should match. Notice it's still a text file. So what you're going to do is you're going to go through and take the test. First question is a tough one. I've had people miss this actually. What is your name? Next question, what is the minimum sum of products equation for the Quinn-McCluskey method homework problem you had? The answer gets put between the angle brackets. So nowhere in your test will you type an angle bracket of any type. So my name is John Smith. I don't remember what it really was. Minimum sum of products equation I got for the problem. I don't know what you got, but I'm going to put mine y is equal to a plus not b. I don't know. Notice I'm going to use an exclamation point for this. Now, when I have finished taking the test, I've done all 100 questions, Then what I'm going to do, or I've probably been doing this all along, is I'm going to do a file save. Then I'm going to go into email and I'm going to send it. But what I need to know is, I need to know that you've gotten this far. You have a text file where you've inserted the correct answers and you've saved it. So give me a green light if that's what you've gotten done. See, I thought you guys were going to do pretty well. Hey, Basanti, I haven't seen anything out of you. Joseph and Kyle, have you gotten yours done? Zachary?
Yeah, I couldn't find the text file, so I'm searching for that.
I'm in the process.
Okay, well, we got to get this done.
Professor, I did P// and then the name of the file along with the website URL, and it's giving me not found. What am I doing incorrectly?
Did you put P1? Capital P1?
Thank you.
Okay, make sure the name looks like this. Okay, there's a P1 here. Later on, that might...
I could not find the text file.
Yeah.
I mean, the list where it is.
This list?
Yes,
Where's your name?
Basanti.
Mm-hmm. You're not on the list?
No, I'm on the list, but I could not find the list where it is. I could
So you're
not
going to go to
locate
the
it.
web. You're going to go to the website, and instead of what
Yeah.
I typed, here's a look like that. And that will download the correct file. If you're having trouble, what type of machine are you working on?
Windows.
Windows, okay. What you can do is go to chat, and I'm sure somebody will be willing to help you there if you're having problems downloading it.
Okay.
So somebody jump on that if you think you can help her out.
Let's check the chat.
What's that?
Yeah. Thank you.
Yeah, look at the chat.
Okay.
Okay. Who am I talking to? Zachary?
Sorry. I'm in the notepad. Am I behind?
You've gotten this?
Yeah,
Okay, fill in the answers.
I did that.
Then you hit save. Now you're all caught up.
Okay.
Okay, now what we're going to do is we're going to email this to the teacher. Sometimes you'll email it somewhere else, but this time you're going to email it to me. So you're going to send it to bostaind@mccc.edu. Send it as an attachment and make sure it's a text file. Make sure you didn't zip it up. Make sure I'm not getting some sort of archive file, some sort of Word document. I want that text file, and that's the only thing attached to the email. Make sure that the subject of your email contains, not an X, contains COS231.010. Make sure the subject has that in it. Otherwise, I may not see it. Now, while you're sending those, and normally what we would be doing is I would tell you when you started the test. Let's say we start a test and it starts at 6:15, and the test is supposed to be over at 7:15. You will have to take the test and have emailed it to me by 7:15. At 7:18, or whatever it'd be, 3 minutes later, I probably won't accept it. In the time in between, you'll be losing credit for being late. So make sure that you're paying attention to time and things when you do this. This exam is an easy one, right? 2 questions, one of them is your name. If you spell that wrong, that'll be amazing. Okay, so let me look at the email that's coming in right now. I don't normally get to see my own email. Somebody else sees it. Ananjit, I have yours. Madeline, oh, that's from the other class. No, Madeline's in this class, right? No, Madeline's in the other class. She's finally trying to get hers in from yesterday. But email it to me and I should see them popping up here on my screen. So I have Nicholas, Vinod, Alexander, Ryan, Simon, Gabriel, William, Zachary, Noam. So they're coming in. You guys are doing okay here. It takes a couple minutes for this to refresh again. But I should feel really popular. I should have 23 or actually 24 emails if everybody's participating. But I recognize one name is missing tonight, so I don't know where she is. Okay. Has everybody managed to turn it in? If you have not turned it in, send me a green light.
Professor, what subject do we put in for the email?
Right over here.
Okay, thanks.
There could be other things there. For instance, if this was an exam, you could say COS231-010 exam 1, for example. But minimally, this needs to be there because this gets scanned when the mail comes in. And anything that doesn't have that, at least coming to this email address, gets sent off to this has to be checked and unspammed and all sorts of stuff. So I don't necessarily see it because I don't read my own mail normally. And they have to realize that it's something I need to see. So, that's why we want to make sure it'll make as direct a path to me as possible. And as this is true, anything you communicate with me with mail, make sure you include that in the subject line. I mentioned that the first night of class, but you guys were still learning how to take notes then. Okay. Anybody still need to send me one?
Yeah, I'm in the process.
I got a couple of Tatiana, I got yours.
I'm still working on sending it too.
Vasanti, I got yours. Okay, I'm sorry to take up all this time, but this is very important when we get to that first exam because you're going to want all the time I can give you to work on the exam proper, not to be talking about how we're going to turn it in. So that's why we're practicing it now one time before we even get close to it. Well, the exam's not that far in the future. It looks like it is because of the way we do units, but some of the units get doubled up on as we move ahead. Okay, let me clean up my screen a little bit here. I got more stuff on here than I know what to do with. Get rid of this. Get rid of this. Get rid of that. All of that. Get rid of that. Okay. I think it's time to move on. Now, I'm assuming everybody did the Quinn-McCluskey problem. I'm not going to do it in class. If you need help going through it, we're getting close to when I'm going to start giving you office hours outside of this. I'm still working on getting a time when the school's not going to have the machines potentially shut down when I'm available. So just kind of keep in mind that we might come back to that as a way of really doing some harder problems. But that particular problem you could check using a Karnaugh map. I mean, it only had 4 inputs. So after you finished using the Quinn-McCluskey, you could kind of self-check that and make sure that it was okay. Now, what we're going to talk about next is something that I call in the components or in the listing for the class, we call it digital components. So let's actually bring up a new window here. If we go to the course outline, we'll see that we're roughly at unit 7. We may get almost done with that, but probably not. We'll probably do some of it in here. There's also a topic missing at the end of this line, which is /MUX for multiplexer. But I'll fix it next time I teach the class. I didn't just now notice the syllabus was missing it. We won't probably get to that. We'll probably get through digital components, arithmetic, and maybe about half of the TTL stuff, maybe more. It depends on how quickly you'll get into it. This is actually, after we do the multiplexers, is kind of the end of the combinational logic where we talk about things which can happen at a particular given point in time, meaning that if I change my inputs, the outputs follow according to some algebraic expression. Once we start talking about capacitors and timers and sequential logic, we really literally are talking about what we call sequential logic. This is where things happen one after the other. And maybe the change in a particular input will cause a change sometimes later in some other piece of output. Or it may be that we need to save a piece of data over time and use it later, rather than what we have now is if we release the inputs, the output changes and we forget what it was. So we may have to have some necessary way, other than just plain old computer memory, of maintaining a bit for some amount of time in the future. For example, if you were running a car wash, you might want to remember that the guy wanted a wax by the time it got to the wax station. But if another car had come in and said they didn't want one, you want to make sure that you don't not give him a wax because he paid for it. So there'll be some sort of a notion of memory or of things in time where we have to maintain bits which may have happened long in the past and realize what the function was now. So we'll get into that with great detail when we move into the sequential logic. And of course, all of this stuff is very prerequisite to being able to do our first microprocessor down here with the SAP1. But notice here's this exam I've been talking about. It's only Unit 16, and while it may seem that we're only halfway there, notice that a lot of these are just one topic units. A lot of these were 5 topic units. So you can imagine we may move through this a little quicker. Certainly I'll pick up just the lecture pace if nothing else, because I've been having to slow down a little bit to get some of the basics under your thing. But if you've worked out and you've actually learned the basics, I don't have to stop, and every time you write down 0111, explain to you that's a binary 7. You'll just know that. Or if I say 2 to the 10th, you know it's 1024. You don't have to think about it. Okay, so digital components, what in the heck are they? Well, when we've been talking about the algebraic expressions that we have thus far, we've spent a lot of emphasis on actually working through the steps in the algebra. And in doing that, we've kind of lost what in the heck would we use this for in a real circuit. And that's where digital components start to come into play. Now, I'll show you a handful, maybe 4 or 5 of them. But you can imagine that there may be many of them. And you can kind of think of this in a programming language as, can you imagine what would it be like if you didn't have some function you could call which could print the result? If every time you needed to print the result, you had to redesign, rebuild, and re-architect the way that's done. That wouldn't be any good. That would be a mess. The same thing is true when we start working with the Boolean algebra statements. For example, we know, let me move this where it's a little more, well, I guess I can leave it like this. We know we've talked about some statements like this. And we've said, well, if we have 2 things which could be true and false and we OR them together, we take their sum, we're going to get a particular value. And we defined this function to have a truth table associated with it. A and B and Y. 0, 0 is a 0. 0, 1 is a 1. 1, 0 is a 1. And 1, 1 is a 1. Well, we know what an OR function looks like. But we might ask ourselves, so what? Where would we ever use this fact? Why would it be useful to us? Is there something underlying all of this, which is really what an OR function is all about? Or is it just simply an artifact of arithmetic? Well, one of the things we could notice with this is that basically the output here is sort of meaningless if A is a 1. Because it doesn't matter what B is, the output remains a 1. So there's almost no use to these second two lines other than to suppress the function of the AND gate, or the OR gate, really. Basically, since this is always a 1 in either of these conditions, it being a 1 doesn't mean much to me. However, do you notice when it's a 0, Y is exactly B? So in some sense, we control whether B passes through to Y by simply setting A low. So if A is set to a low value, whatever B is immediately seen at Y. So this is an interesting behavior. The other behavior we can see is really the only interesting line in this truth table is the first one. If both of them are zeros, the output is 0. So conceptually, when we look at this, this gives us some sort of underlying function that this has inside of it that it's trying to get out and tell the world. Yeah, it has the kind of boring truth table, but I think it's more impressive that there's this thing that says if both of them are false, the output is false. There's something important going on there. And also, if A is 0, B could pass through the function without any changes to it. I kind of like that. That's an interesting behavior. We also looked at this and we said, yeah, we also know there's a dual to this. Since we have one thing we proved true, we could also say that Y is equal to AB, and it'll be true, but it will be a different truth table. Let's write a truth table for that. I have to do a lot of tabbing here, but I'll make it tidy for right now. A and B, and we have 0, 0, 0, 1, 1, 0, and 1, 1. Now, using a similar way of thinking about it, let's write in the outputs for an AND gate. Oops, I'm on the wrong line there, aren't I? Okay, look at that for a second and think about what is there outstanding about this particular table? What are the interesting fact that's in it that we're trying to get out so we could use it as kind of a subroutine of function? What sort of thing might I need to do that this does well? And if I had an interesting state, which one is the interesting one? Nicholas, what do you think is the interesting state?
If I had to take a guess, it's probably the last one. The if A and B are both 1, then Y is 1.
Yeah, that's the one that's interesting here, because this gives us something that's not a 0, and it's the only one that does that. So it's a good answer. In this case, it's a little different than it was over here, but it has the same idea. That the one that is very interesting to all of us is the fact that it's always false unless, and the unless is both of them are true. In this case, it's always true unless both of them are false, in which the output is false. So one is kind of the inverse of the other in terms of thinking. Now, there's another interesting line in here. Robert, what is it?
I guess it would be if A, B is off, Y is off.
Well, in this case, I didn't write Y at the top, or else I accidentally erased it. But in this case, it's almost always off. So let's take the other way of thinking. If A is a 1, notice that Y exactly matches B. So it has a very similar function to what we had over here, where B passed through if A was low. Over here, B passes through if A is high. So we could imagine that if we wanted to block a signal with this AND gate, we would simply put a 0 on the A input, and then the B input wouldn't matter because Y would always remain a 0. So somebody looking at this output wouldn't know what the values of A and B are. Now, if they, however, saw A and B, or they saw B changing because they knew A was a 1, they would know that the data had passed through and they were actually reading the real value of B on Y. So now, while that may not have much meaning to you right now, think of it as a kind of a fundamental. The first time you ever figured out, my cat does it all the time. She has figured out that if she goes, sits, and stares at the treat bottle long enough, I'll give her a treat. Same thing here. This doesn't have a lot of function, but we're learning that if we discover interesting states, we might be able to use them later as some form of meaning, put meaning to them. Let's change this first equation. I'm going to write just a second set of outputs on it here. What would we do if we inverted all of the outputs from this? So let's do that. This function right here was an OR. This function right here is a NOR. Remember, a NOR is simply find the OR and then invert it. Notice here, which is the interesting state? Well, it's the same one. 0, 0 produces a 1. All the others produce 0. Interestingly enough, if A is a 0, notice that the output here is the inverse of B. We've inverted B. So using a NOR gate, we could actually invert the value of B under the control of A, meaning it's not going to be inverted. It's not even going to be seen if we make A a 1. It, however, is going to be the inverse of it if we make A a 0. So there's a function we could use. We also could do the same over here. I'm not going to bother. Well, yeah, well. I'll write it out as well. If we take the NAND function, because we are using a lot of NAND gates, notice again that we get, if A is a 1, we get the inverse of B out. If A is a 0, we just always get a 1 out. So one of those 4 truth tables could turn out to be useful in a particular circuit. Interesting one here, of course, is the last one, that if both the inputs are 1, the output is a 0. We don't care about the fact that it's true all the rest of the time. We care when did it change to something else. That's when it becomes a more interesting component. So let's take one of those and actually implement it as a circuit. Let me see, can I do that from here? Okay. Well, what I want to do is I want to implement it with a circuit. I'm going to create something called a register. We'll worry about registers a little later when we're talking about sequential logic, but basically they're a thing that can remember what bits used to be. And in this case, it's remembering what bit A, B, C, D, E, and F are. There's 6 inputs here, or outputs. These are outputs. We're going to use AND gates here, just as we said in the last table. Remember that the truth table for this, we take A, we take B, we're going to produce a Y, 0, 0, 0, 1, 1, 0, and 1, 1. The outputs for these are going to, of course, be 0, 0, 0, 1. Now, in this case, we see an A and B here. These A and B's are not those A's and B's. Isn't that confusing? Well, that's the way life is. The A and B we're talking about here are the A and B for each gate. So this is A, this is B. It's unfortunate they're named the same. This is B. This is A, this is B, and so forth. So for each of the 6 bits, we apply this function. And this function says that the only time B passes through would be when we use these 2 rows right here. Okay, now, I actually labeled this backwards to the way I built the chart. So I'm going to put the B in the first column, the A in the second column. Does that distress some of you? You OCD people that need things in order? Sometimes it bothers people a lot when things are out of order. But that's fine. We have a B, we have an A. In this case, if B is held high, A passes through. So this is B over here. B happens to be hooked to all of the gates on the right-hand side. It's the thing that's doing the blocking. A, on the other hand, is the A component here, and it will either pass through as a 0 or pass through as a 1, but only when B is high. So if I assert enable, meaning all of the B's become 1s, and these values here get asserted onto the gate, we know that whichever ones have 2 1s will produce a 1. So here's 2 1s, that's going to be a 1. Here's 2 1s, that's a 1. Here's 2 1s, that's a 1. And all the rest of them will be 0s. Zero, 1, 1, 0, 1, 0. So whatever these outputs were, now these guys match that. Let's assume that see if I can get backwards with that fast enough. Let's assume this is a 0. Well, if it's a 0, every one of the gates has as one of its inputs a 0. Which, if we look at our truth table, if B is a 0, it means it doesn't matter what the other guy is. A 0 is going to come out the other end. So let's put 1, 0, 0, 1, 0, 1. A 1 and a 0 is a 0. A 0 and a 0 is a 0. 0 and a 0 is a 0. 1 and a 0, 0. 0 and a 0 is a 0. 1 and a 0 is a 0. So if this is low, we're not enabled, you don't see the register. If, however, this is held high, whatever those values were are seen on the Ys. Anybody have any questions about that component? Okay. Moving ahead. Another interesting component that we might deal with is an exclusive OR. Now, I guess I need the ability to do a picture here again for you. An exclusive OR, when drawn schematically, looks like this. It has 2 of those curvy things on the bottom. Now, we would not ever build one this way. Instead, we'd build it out of Nand Gates, but we proved one night we could, so that's good enough. The function for this, again, if we have an A and a B input, says that if one of the inputs is a 1, make the output a 1. If none of them or both of them are a 1, are the same, make the output a 0. So basically what we said is we want our truth table to look like this. It's close to a regular OR. A regular OR would also have a 1 here. It's called an inclusive OR, whereas this one is called an exclusive. E-X-C-L-U-S-I-V. E. Exclusive, meaning it excludes the outside ones, only these. Now, interesting, if we were to look at it as an interesting thing, is we would see that when the inputs match, the output is false. So that's an interesting thing to know. That means if we were comparing two things for equal, we could tell when they were different by just looking for them to not be false. However, more interesting than that in this particular case is the fact, let's take and use either, let's use B, I guess. Well, we use A. I'm going to relabel these as B and A just because we're going to relabel them in the next table as well. I want you to notice that if B is a 0, the output exactly matches A. If B is a 1, the output exactly matches the inverse of A. So I can use B to control whether the bits that are going into the A input get inverted or not inverted. So there should be a component that can do that. That's something you would want to do fairly frequently. So in this case, we have an 8-bit register. Remember, these A's just happen to be named A. There's nothing special about them. They're not really the A of these gates. Each gate has its own A and B inputs. But in any event, A passes directly through, as long as in our picture this invert signal is called B. As long as, so here's our truth table again, just so we can see it at the same time. Notice it has two halves to it here. So if B is a 0, we're in the top two lines, A passes directly through. So whatever A7 is, Y7 would be that value. What A6 would be Y6. So exactly the value passes through as long as invert is a 0. If invert, which is the B signal here, becomes a 1, however, then the opposite comes out. I put a 0 in, a 1 comes out. I put a 1 in, a 0 comes out. So this basically is a function that can do something which we talked about when we were talking about a 2's complement, which is called the 1's complement. I won't write it out. 1's complement. That was the first step of doing a 2's complement. Remember when we were going to do negative numbers? We basically took a number and we said invert all the bits. Okay, I can do that. And then add to that a 1. And the number you get, which is in this case 1011, is the negative version of whatever that is. So this version is a 5. This number would be a negative 5. So this circuit right here does the first part of this conversion. It flips all the bits. We'd only have to figure out how to add 1 to it to be able to take something that could turn positive things negative and negative things positive. That sounds like a useful component. Sounds like something we'd want to know about so we could use it, particularly in arithmetic, inside of a microprocessor. Anybody have any questions about this controlled inverter? Tatiana, what is the signal we use to control it?
I'm sorry, I didn't hear the question.
What is the signal we use to control this? It says down at the bottom, controlled inverter. What's controlling it?
Sorry, Professor, I'm lost here.
Anybody want to help her out?
It's B, right?
Right, B, the invert signal. In our chart, it was called B. We could have just as well labeled this invert, right? So you could say invert right there. Notice my careful Mayan text rather than Unicode. Okay, so we now have another unit we could use. We have something that can block things with an AND gate. That's a very important function to realize, that if you ever want to make sure a bit gets turned off, even in programming, you can block the bit by ANDing the bit with an AND gate and taking one side be the bit you're interested in blocking and the other side being a bit that says block it or don't block it. Use it a lot when I'm writing code, you know, like software programming. Okay, get rid of this. Sure, I can get rid of this. Ah, that's terrible looking. I wonder if I can do this. I've been wanting to do this for quite some time. Nope, can't do it that way. But I can do this. Nope, can't do that. But not to be, do that. That might work. Hey, look at that. Once again, I am the master of all things paint.
If you press Control N, it's the same thing.
Yeah, I know. That was what I just tried and didn't work.
Oh, okay.
Okay, so well, and that's probably my machine. It's not necessarily anything wrong with it. I have a lot of remapped pieces of code. Okay, let's see here. What is this window I have over here? Have I deleted everything in the wrong window? I did. Okay, so let's look at another thing that might be interesting. How about this guy? Okay, we can read what it says at the bottom, except for at the very bottom they ask us a question about it. So that scared me for a second. Maybe I have to put an answer up here. Let's talk functionally about what this does. We know everything. Any one of you, minus whoever in there is, you know, got funny little circles next to your name, probably have figured out already what this does. But let's pretend like we didn't. Remember the bus we were using when we built things with Nand Gates or any type of gate? We ran an A line down, a B line down, a C, a D, and then we inverted each one and created a not A, not B, not C, and a not D. What this circuit wants to do is it wants to have a 4-bit value put into this register up here. 0, 0, 0, 1. 0, 1, 0, 0. Whatever the 4-bit value is. And then it wants that particular input, and only that particular input, to be turned on. So if I look at these, let me see, do I have, I think I'm using the wrong tool here, but what the heck. If I want this guy to be a 0, and this guy to be a 0, and this one to be a 0, all the way down, I have to then say that I want to make sure these NAND gates, or AND, these are actually implemented using ANDs, never have all 4 of their inputs turned on. Because if they have all 4 turned on, a 1 will come out. Now, we haven't seen a 4-input AND gate, but we can imagine what it is. All of the first 15 lines, 0, 0, 0, 0, up to 1, 1, 1, 0, have a 0 coming out. And the only time this gate's going to produce a 1 is if all 4 inputs are 1s. I mean, we can just deduce that because we're smart people. So, in order to get 1 turned on, what we would really need to do is we'd need to make sure that when we want 1 on, that its inputs are all tied to signals which are currently on. So let's take and put a value up here in the little box and see how we'd go about doing that. Let's say we wanted 0, 0, 1, 1 to turn on. This would be the 0. Oops, I can't write on that. 0, 0 gate, the first gate, second gate, third gate, fourth gate, fifth, sixth, seventh, eighth. Eventually we get down to the 9th gate, right? So this is 0 here. The gate we'd want to have turn on if we put a 3 up here is the 3rd gate. So we want to make sure that the values here are hooked up in such a way that they're only turned on if we have 0, 0, 1, 1. So let's set that up and see what things are worth. If I have a 0 here, that means the first line is equal to 0. Its inverse is a 1. This guy has a 0. his inverse is a 1. This guy has a 1. His inverse is a 0. He has a 1. His inverse is a 0. So what we want to do is go down and look at all the gates, and we want to see if any of them hook only to this line, this line, this line, and this line. So scanning down, we look at the one we think it's going to be, and let's check it. This is okay. This is okay. This is okay. That's okay. So by crackies, this guy is actually hooked to the ones that would be turned on. And if we look at every other gate, none of them, other than this one, are hooked to those particular lines. That must mean that the first one is hooked to all the inverses. Not A, not B, not C, not D. It was, in fact. The next one should be 0, 0, 0, 1, so it should be not positive, right? Not A, not B, not C, D. Not A, not B, C, not D. So literally, these are wired up in such a way that they're hooked to the binary lines that will be asserted when we need a particular one turned on. This is called a 1 of 10 decoder. Basically, there's 10 lines. Only one of them will be hot at any given moment. Because there's 10 lines, we need 4 bits to address them. Notice 3 bits wouldn't be enough. 3 would only get us from the first one through the 7th one. We need 4. But that does beg the question of what happens if we put a number bigger than 9 in? What if we were to put 10 in? Would any of the outputs be turned on in that case? Samana, what do you think?
I don't think that they'll be turned on.
Why not?
You probably need less than that.
Okay, Peter, what do you think? Help her answer out there a little bit.
Oh, wait, were you calling me?
Well, I was, unless you were asleep.
No, I was paying attention. I'm just not entirely sure.
Okay. You have missed several classes, so that may be part of it.
Yeah.
Kyle, how are you doing that one?
For a 10?
What if I put a 10? What if I set the bits up to be 1, 0, 1, 0? Would all of these be off?
Yeah, because when they change.
Anybody else want to? Anybody else want to have a Gabriel? Can you submit some sort of insight on the problem here? Which one? Okay.
C.
Well, this looks like this is a 10, so it's the letter A. So it has a 1, 0, 1, 0. That means somebody has to be hooked to A, not B, C, not D. Well, we know it's not him, it's not him, it's not him, it's not him, because all these guys are hooked to whatever their number is. We get down to 9, nobody was hooked to this combination, so none of these would be turned on. Wouldn't be illegal for this to be a value, it's just you get no result. So if you think about it, this is kind of a don't care state, right? Because it can't produce an output. Neither can 11, 12, 13, 14, or 15. If any of those numbers appear in this register, none of the outputs would be turned on. Okay, anybody have a question about this? This is a fairly important one because this also will lead us later into multiplexers and into demultiplexers and a couple other decoding type of devices.
Professor, I don't have a question, but Simon is saying that he's having like severe network issues. So.
Which Simon Long?
Yeah.
Okay. Okay, so I think we'll move on to the next I got to keep my eye on the clock because I know I have a time and we have to meet. Let's look for a second. And I'm not going to do all the detail of this one because it doesn't really need it, because there's a couple things in here that I'm going to kind of leave you with. You can look it up on your own type of thing. This particular one is an odd parity generator. The idea is we have 7 bits here. Remember ASCII? ASCII is really a 7-bit word, and we add an 8th bit for parity. Well, the bit we're going to add is the one down here. This is going to detect whether or not we have an even number of bits turned on or an odd number. Now, this bizarre looking thing here is basically a multi-input Zorro gate. It has 7 inputs. I don't expect you to understand exactly what its function is right now, nor do I have the desire to write out all 128 lines in the table. Just be aware that if we have an odd number of bits, this will turn on right here. So if it's an odd number of bits, that will turn on. If we have an even number of bits turned on here, it will turn off. So on odd it turns on, even it turns off. So if it's odd already, we want the bit to be a 0, right? So it stays odd. But we would have a 1. So we need to invert it one more time, so this actually is the odd parity bit. So if there's an odd number here, produces a 1 here, we invert it to get a 0 here, which is what we send right there. So if this had an odd number of bits already turned on, it would detect that it was odd by giving us a 1 right here. We would then turn it into a 0 by inverting it and send it as the parity bit. By the same token, if we had an even number of bits right here, it would say, well, it's not odd, we got a 0, but we need to add a bit. So it would turn this output into a 1. We would send the 1, and now we would have 1, 2, 3, 4, 5 bits. So with this simple circuit, although it looks complicated because this thing looks like, you know, a rocket ship that went bad, or else a bad haircut, not sure which. And we would just simply hook this up and we would generate the odd parity. So it's really a simple thing to do. If we needed even parity, we just don't include that last piece. And this could be built in a circuit that needs to send ASCII data. We would send it in this order, of course. We'd send, you know, from low bit to high bit. But when we calculate the parity, we'd have all the bits in a row like this. Anybody have any question about that?
Sorry, I have a question, but not about this problem. Do you see the raised hand notifications? Because I had a question about the previous problem, but
no, I don't. I don't see any of those sort of things because they're on a monitor that's about 15 feet away from me.
All right.
So the only things I actually see are I see if your microphone comes on if I'm looking. If I happen to be looking at a different screen, I don't even see that. What was your question about the last problem?
Well, I just thought that this thing would be on, and I just wanted to ask you about that, but it doesn't matter, I guess.
Okay. Okay, so let's bring up another one here. That guy's fairly straightforward. This is a fairly interesting one. And again, I'm not showing you every possible digital component, but I'm giving you some ideas of if you were designing circuits and things you might want to have. This one, if I can figure out how to make it wider, is going to compare 6 bits against 6 bits. I accidentally drew on it the other day, which is why this line doesn't exist. So I have a register containing 6 bits. I have another register containing 6 bits. Their outputs are connected to this. So the A5, B5, both come into this guy. A4, B4, both come into this. When we're all done, they're compared using an AND gate with 6 inputs. Again, all of these have to be a 1 for this to be an equal. Otherwise, we get a 0 and we consider it not equal. So if you ever had to compare two things, this is a great circuit to come back to and think about. We actually talked about it when we were looking at the functions, but we never really saw anywhere place where we had actually used it. Oscar, what type of gate is this?
Is that a NOR gate? It's like the OR gate, but it's inverse.
In fact, is exactly what you said. It's NOR. Now, this isn't an exclusive NOR, but it really doesn't quite do that function exactly like that. What it does is it does a XOR, an XOR, and then inverts it. Now, the reason for that is because the table here is much handier for the XNOR. And we usually say XNOR. It sounds like you're snoring or something when you say it. Some people say XNOR, but that doesn't sound cool. Now, if you recall, exclusive OR itself went 0, 1, 1, 0. So since this is the inverse of that, we want to go 1, 0, 0, 1, which is ideal for us here because now if A and B are equal, this will produce a 1. And remember, we need all of them to be 1s if everything is equal in both of them. So let's assume that this guy had a 0, 1, 1, 0, 1, 0. And this guy had a 0, 1, 1, 0, 1, 0. Each of the gates would look at its own A and B. So this gets 0 and 0. That means it's true, produce a 1. 1 and 1, that's true, produce a 1. 1 and 1, true, produce a 1. 0, 0, true, produce a 1. 1 and 1, true, produce a 1. 0, 0, true, produce a 1. All of the inputs to this are true, equal. Let's pretend like this guy as the last character actually had a 1 here instead. This would be a 0 because they're not equal. This would not have all 1s in it. It would produce a not equal condition. So that's a pretty handy circuit to have. You can compare one set of bits against another set of bits and know if they're identical. You can imagine in programming, a part of an if statement would include something that lets you test for equality. Like in C or Java, C++, you use double equal, right, to look for equality. Anybody have a question about this one? This is actually kind of simple, but because it uses the XNOR gate, which Oscar knew about, which was excellent, we usually save it a little while to show people.
I just have a quick question.
Sure.
So this one compares 6 bits to 6 bits, but can it compare any number of even bits? Like, for example, if I wanted to compare 10 bits to 10 bits.
Yes, it could.
Okay.
It doesn't really care. The only thing that's important is you have an AND gate at the end, which only turns on when everything is a 1. So let's assume I had 12 bits and I could only find 6 input AND gates, right? I would build a second one right beside this one, which had, I'm not just abbreviate these, 6 of those going to the other 6 bits. I would, hook them all in down there. And then I would take these 2 outputs and I would combine them as inputs to a single 2-input AND gate, and its output would be the one we call equal. So as long as all of those are equal, this guy would fire equal, and all of those are equal, I would fire them equal, and I even use the word and. This guy should then say equal if every one of the 12 matched. And yes, indeed, if we had a 64-bit computer, we might want to compare 64 bits of one word against another 64 bits using a circuit like this. Anybody else have any questions before we move on? Okay, we're going to move on now to a slightly different topic, which is arithmetic. And I'm not going to do an exhaustive look at this, but we're going to first of all develop the equations for it and then look at implementations of that would be practical. What's that? That's paint. Get rid of that for the moment. So let's say that what we wanted to do was we wanted to add up some numbers. Well, we're going to take and do like we would in decimal arithmetic, and we're going to add the rightmost column up, and let's just for now call the top line values A and the second line values B. We could build a little truth table for that. We could say A and B are the two possible things that could occur, and we'll call our output, instead of Y, we'll call it sum. And what's the sum of those two? So we have 0 and 0 going in. Our sum could be a 1. No, I'm sorry, 0. What am I looking at here? 0, 1 coming in could be a 1. 1, 0 coming in would be a 1. 1, 1 coming in would be, the sum is the number we actually get if you add 1 and 1 together is 2, right? 2 won't fit in one bit. So the actual answer is 1, 0. But we only have one bit to put it in. So we're going to call the sum that 0, and we're going to create a second output. We'll call it carry out. I feel like I'm at Burger King. And for all the first three, we basically did not have a carry. But for the last one, we did. Because we know, oops, not a 2, 1. We know that if we added a 1 and a 0 here, we just get a 1. But we know if these were both 1s, we would put a 0 underneath it, but we carry a 1 to the next column. Now, without doing much thinking, we can actually look at the equation for that. What function do we have that has a truth table that's exactly equal to that? Somebody just tell me online.
And that's an AND
Yes,
gate.
that's an AND gate. So really, C out is equal to A ANDed with B. Sum is equal to something. What function is this? Just somebody tell me what that function. We've seen it already about 3 times tonight.
Exclusive
That's an
OR.
exclusive OR.
Right, that's an exclusive OR. So what we could say is we could say A exclusive OR B. Now really, we would put a circle with a plus sign in it, but I don't have that character on this keyboard. So I'll just write out Zorro. So our two outputs have different functions, but we can easily describe the functions. We could build this. I mean, we already know how to put an AND gate in a circuit. We could draw one with a Zorro in it. We'd then later convert it into a NAND implementation, but it really wouldn't be very hard. Let me see if I can find over here a quick picture for us. Wouldn't be hard for us to hook those together like this. A and B coming in, they produce C out or carry by using an AND function, and they use an exclusive OR function to produce a sum. We know we could turn this into a minimum sum of products because all it is equal to is Y is equal to not A, B, or B not, or A not B. We know that because the fundamental products of those two rows, that's the two rows that are true. So we could turn this into something that was implemented this way, but this is an elegant way of drawing the picture. This, however, has the name of half adder. You might wonder, is there such a thing as a 2/3 adder, or is there such a thing as a something else, like maybe there's a full adder? This is half a 1, we want a full one. The answer is yes. And the reason for that is that when I produced both of these as my outputs, and I start thinking about the next column doesn't just add A and B together, does it? It also adds in the carry. So if we were to think about it for a second, we have carry in, we have A and we have B, and they're going to yield a carry out and a sum. So carry in could be a 0, A could be a 0, B could be a 0. We generate 0 for the carry out and 0 for the sum. 0, 0, 1. There's no carry, the sum is 1. But is it the 1 there? There's no carry, there's a 1. Now we got a 2, so there'll be a carry, but the sum would be a 0. What if carry is a 1 and all the others are zeros? Well, no carry, but we get a 1. How about this? Well, we get the number 2. How about that? This. Again, we get the number 2. And finally, we might have all 3 of them turned on, which we get the number 3. So if you look at this, we once again have a set of truth table entities, which we kind of can see built in here. If you look at this guy, the first 4 lines, I can't highlight them, but the first 4 lines are really an exclusive OR. The last 4 lines are really an exclusive XNOR or XNOR. In the carry out, the first 4 lines are an AND. The second 4 lines are an OR. Okay, let's see if we can do a little Karnaugh reduction to this guy. I mean, that sounds like something that might be more fun than we could possibly imagine. By the way, if you guys are bored with this, or it seems like it's putting you to sleep, or you can't pay attention, you're in the wrong business. This should be exciting to you. You need to look at this and think, wow, we're able to do this. That seems so simple, but we know how to do it. And you get a lot of people that can blah, 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 talk about data science and stuff like that, that haven't a clue as to how to make it work. You know, computer science is a very, very important field, but it really requires a lot of dedication, a lot of attempt at learning. It doesn't just fall on you. It's not, everything is not just obvious. So let's build 2 Karnaugh maps here. Since we have really 2 truth tables built into one, we need 2 Karnaugh maps because you need 1 for every output. And remember, if we separate this into parts, whoops, I can't draw on this, but the dotted line goes between here. So if we were to label this, this is not CN, CN. This is A, not A, not B. This is not AB. This is AB. And this is A not B. By the way, somebody asked me a really good question the other night about the Karnaugh maps when we were talking about how they went into 3 dimensions. One of the things I had to explain to you and didn't give you the entire detail because it becomes much, much more complicated is we looked at it in terms of 4 planes sitting on top of each other. So we were actually viewing the cube only from one side. There's actually 6 sides you can view it from. And when you do, think about the relabeling that has to go on all the squares. But a thorough examination of one involves you actually turning it into all 6 orientations. So you can look for the adjacent things that are on the surface a little more easily. We'll talk about that later when we have some multi-dimensional problems. Okay, this guy I'm not going to label for the moment. He's got exactly the same labels as this guy. So let's put in the first table C out. It's 0, 0, 0, 1. 0, 0, 0 over here, 1. Then 0, 1, 1, 1. 0, 1, 1, 1. Well, it looks like we could combine those 2. We could combine those 2. And we could combine those 2. So the answer here, which is our Cout, is equal to Cn not A, B, right? Well, no, we're not going to need not A because it changes in the red box. So the red term here is going to be CnB. Or the green guy here is CnA. Or the blue guy, Cn changes, is just AB. So that would be a fairly straightforward thing to wire up. It's three things ANDed together. They're all ORed together. Well, I should say two things ANDed together and three of those ORed together. The other guy, if we fill him in 0, 1, 1, 0, 0, 1, 1, 0, then 1, 0, 0, 1, 1, 0, 0, 1. You'll notice nothing can be combined here. There is nothing that combines. There's nothing vertically, nothing horizontally. So we're stuck with labeling each of his things. But we also, by observation, can probably deal with him, thinking about him being a Zor or Znor. So let's look at how you would implement this full adder in a circuit. Basically what we would do, here's our three ANDs. They're hooked to A, B, and carry in. And here's the carry out that we produced after they're ORed together. So that's exactly what we derived. The other guy, turns out that you can use a 3-input Zorro gate. We didn't talk about the details of that, but it does exactly that function that we illustrated, and it produces the sum. So A, B, and C now can be added as a full adder. When you're adding numbers up, if you remember, we've got a first column on the right, which can be done with a half adder, and all the rest require a full adder. So basically what we're talking about when we say that is something that looks a bit like this. These are just block diagrams now. Full adder contains that whole circuit. Half adder contains the previous circuit. But we take an A and a B to be added, producing both a sum and a carry out. After we leave the half adder, all of them are full adders because they take a carry in, an A in, and a B in, producing a sum and a carry out. And this would be extended with full adders till the cows come home, however many bits you need to add. Now, if we were to implement this in circuitry, these boxes just stand in for all the circuitry we saw in the other picture. One way we could do it, which is kind of interesting, makes use of some of the components we had talked about earlier, or at least one of them, which is this. If we made all of them full adders, and we took B and ran B into an exclusive OR gate, and we had a signal going to that exclusive OR gate, thinking back to what we did, this is simply a controlled inverter. B gets inverted if subtract is asserted. So if this is a 1, that's a 1, that's a 1, that's a 1, B coming out the other end is the opposite of what it would have been. That's the first step we need in creating a 2's complement or a negative number, or taking a positive number and subtracting it. Well, where do we get the other 1 from? Well, we can get it by forcing the carry in of the right guy here, who normally is a full or half adder. Let's just make him a full adder, and we'll make his carry in normally be a 0. But when we're doing a subtraction, we'll push an extra 1 in, which is exactly what we need. Flip all the bits, plus add 1. That circuitry there will do a 2's complement so that this becomes an absolutely functional adder-subtractor. It can do both addition and subtraction, in this case of just a 4-bit number, but we could extend it many bits if we needed to. This will actually be a circuit as part of our first multiprocessor, our microprocessor that we designed. So you'll want to kind of look at that and kind of appreciate and understand that we're using a controlled inverter, and then we're also using a full adder on the right instead of a half adder, which gives us the ability to add in an extra bit when we need to. Anybody have any questions on the arithmetic? We need to move on to the next topic. I'll post all of these pictures I've been showing in class. Not sure whether I'll put them on the website or I'll put them on Blackboard, but they'll appear one of those two places somewhere in the next couple of days. Okay, let me see if I got any stray stuff opened up here. That guy is stray at the moment. Okay, we're going to talk about technology for implementing many of the circuits and things we have been talking about. I have often told you when we implement things, we're going to use 2-input Nand gates. And I've described a gate as being something that has inputs and outputs and basically follows some Boolean rule to produce a truth table. We know the gate function for that, so we won't even bother repeating it here. We also know what the schematic looks like. It looks like an AND gate with a bubble on its nose normally, but it can also look like an OR gate if we put bubbles on its inputs. That would be the De Morgan version of a NAND gate. And I've promised you that we could build anything in computer science using them, so we'll focus on them for a moment. Many, many years ago, 1947, 48, somewhere in there, the transistor was invented and really revolutionized any type of electronic devices of the time. It replaced vacuum tubes, or what were often called valves at the time, and eventually we were able to produce them at a pretty high rate in terms of density, but they still were fairly big. Round about the 1970s, probably a little earlier than that, there was tests and things done, but they came out with something called an integrated circuit, which we will call an IC, and it stands for integrated circuit, which consisted of a bunch of NAND gates or any other gate fabricated out of transistors which were grown on a silicon wafer and then packaged inside of an accessible package that had pins on it. The ones we're going to be dealing with are more modern, and the technology we'll talk about is a little more modern, but we're nevertheless going to be using ones that are in something called a DIP package, a dual inline pin package, and they have other names for it, but typically that's what that would stand for, meaning that it is a through board, and that's sometimes called a PTH, a through hole, pin through hole, or some other names are used for the P, depending on the vendor. But the integrated circuit we talk about, in particular for ours, is often called a 2-input quad NAND gate. What that means is it has 4, that's the quad, 4 gates inside, each of which has 2 inputs. Additionally to that, each will have a power and a ground connection available on it. If I were to show you a picture of that, I think, see if that's it. Nope, that's the wrong lesson. It would be this guy. It would look like this looking down on the top of it, except it would be all black and you couldn't see what was inside of it. Pin 1 is up on the left-hand side normally if you mount it and look at it that way, in the hierarchical way. One end will have a little slot cut out of it, or a square, or maybe nothing there, but there'll be a little circle or a little dab of paint. There'll be something that indicates where pin 1 is. You count down that side and then back up the other side. This is a 14-pin chip. We needed 12 of them for the gates. So it's 3 times 4 is 12. Plus we need a pin on the bottom left corner normally to be a ground pin, and on the top right corner to be the voltage that goes into all of the gates. This is where power comes from. If you look at the picture, pin 1, pin 2 are inputs to a gate who has an output on pin 3. These pins go through a board and are soldered onto the board from the other side of the board. Once their in power is applied, they serve their function, and you would hook up the pins and you could observe what the output voltages and things are on these. The particular technology we're using is something called TTL, which stands for transistor logic. It has 2 transistors in it because it uses something called a totem pole output. Think of the totem pole that the Native Americans use that has boxes of items stacked on top of each other. On the output of a TTL chip, many of them, not all of them, there are a few that aren't, but there'll be something called a totem pole transistor outputs. And what that means is I'm going to see 2 transistors basically stacked upon each other at the output. One or the other, but not both, will be turned on, and the other one will be turned off. We'll see that later when we look inside a chip and try to figure out what the circuitry does. Now, these chips, being TTL, surfaced around the mid to late 1970s and are still in use today. And when you look at a package to determine the name of one, there's an order for naming them. First of all, the manufacturer ID comes first. SN happens to stand for, believe it or not, Texas Instruments. You might go, SN, Texas Instruments, what were they thinking? Well, there's reasons for it, and too complex to go into now, but it's not TI, it's SN. The next thing in the label, for at least the TTL chips we're going to be using, will be the number 74 or the number 54. 74 means commercial grade. 54 means military grade. The difference being the temperatures they can withstand, the shock absorption they can have, also the voltages they can tolerate, and sometimes the amount of current they can take without being damaged. The next thing I'm going to just simply call the technology family, or none. May or may not be there. Some examples of that might be the letters LS, the letter S, the letter ALS, the letter HCT. There are various things in there which are different ways that the technology is actually done since the original TTL chips and their specifications were defined. The next thing is a number, and it's the function of the chip. 00 means NAND. We'll talk about some of the others if we need to. Then finally, it may or may not be present, but the type of packaging may be indicated. For example, N means dual inline pin. In particular, it means a plastic dual inline pin. If I were to give you the name of a chip and I put, I'm going to make one up that's not real, XY 54 BZ 123 Q, you should be able to tell me what the parts are. It would be made by the XY company. It's TTL and it's military grade. It uses the technology family BZ, which doesn't really exist. Its function is 1, 2, 3, which I don't know what that is, if it even really is a function. And finally, it's packaged in a Q-type package, which I don't know if such a thing exists, but perhaps it does. Oops. The one we're more likely to encounter is an SN (7400), possibly N on there, but I'll leave it off for now, or I'll put it on there. And that turns out to be a standard family. Notice there's no alternate family between the 74 and the 00. So there's no technology family. And the 74, which leads us to say that it's a commercial grade chip. This might be a chip we'd actually lose. As a matter of fact, if we were having class together, I'd bring some of these in, we'd build something. However, let's look and see if we were going to actually want to get one of these sometime. How would we go about doing that? Let's go somewhere that sells them. www.digikey.com, for example. Let's search for a Nand Gate. Let me have to hit that button. Here's the list of what it found. We want a logic gate. So there's two sets of them here, but this says these are fancy ones. So let's just go for the not so fancy ones. And then over here we can decide what are the things we want. Well, we want a NAND gate for sure. And we want it to be through hole, meaning it goes through the board. And let's just say we want them to have it in stock. So let's apply the filters and see what we get. Well, it looks like there's all sorts of chips. Notice here, SN74LS00N. That's really close to what we wanted, isn't it? It's in the LS family, not the no alternate family. But we'll pretend like this is, good enough for us. Here's what the chip looks like. One's right side up, one's the other side down. Pins go down and through the board, and then they get soldered on the other side. See the little notch on the left-hand end of it? That's the thing that says pin 1 is going to be, if you're looking at the top and you're looking at the notch, it'll be to your left. I can't point at it and point to the thing that keeps it up, or it'll make the picture go away. And then there's some data sheets in here that will give us some interesting information about this particular chip. So we didn't find literally what we wanted. So let's go back and let's search all products literally for what we wanted and see if such a thing even exists anymore. Remember, sometimes the newer families are more. Let's actually search for an SN7400N. Well, it looks like they've got one of them is through hole, but it's in a package we don't want. Well, no, that's not exactly true. I think if we pick through hole and 14-pin dip, we're going to be pretty close to what we want. So let's look at that. They have one chip, one type, so they don't carry many of them. If we were to go buy one, let me see if we can, here's the pricing over here. They cost $1.60 each, which means if I could buy them in bulk, so for instance, if I were to buy 1,000 of them, I'd get them for 73 cents each. If I were able to buy 5,000 of them, I could get them for 64 cents each. So they get extremely cheap as you get bigger. If I were to get the LS version of this instead of the let's go through hole, PDIP. I was saying already, this guy right here is only 23 cents each. So because people use more of them, and because this one is, what's the difference between the two? really just the manufacturer. This is a manufacturer that manufactures for Texas Instrument. So they're able to use the real part number. But in fact, DigiKey sells it with a slightly different part number because they can sell it for a lot cheaper. Is this chip just as good as this one? Well, we'd have one problem if we tried to use it. The problem is right over here. It's obsolete, meaning that they don't even carry it. They have 0 available. However, if we were to look, nope, they don't even have a date. So although they still can probably service it, meaning all the data sheets and everything are here, if they were to happen to get some for whatever reason, repackaged or whatever, they're going to sell them at 23 cents each just to get rid of them. So that's just kind of a way you could actually use the internet to go look around and see how these things look. The data sheet, which is where we're headed next. Let me blow this up a little bit. And give me a green light if you're sitting there and you're happy. Give me a red one if you're not happy. Let me see if the usual people are missing. Yeah, they don't think I catch them, but I do. Okay, look here now. This is the first page of the data sheet. This data sheet is for lots of different types of the SN. They could be 74s or 54s. They could be no technology alternate family. They could be an LS or they could be an S. They're the quad 2-input positive Nand gates. They put the positive here to mean that the logic is NAND if you treat it as a positive gate. Because obviously if you treat it as negative logic, it's going to be something else. So all of these are covered in this particular document. The important things down here is they say the sorts of things they could be used for and some features and some things. So it's kind of a sales sheet. But they give us the function that can be performed. And there's our two De Morgan form. One is NANDing it, and the other is the De Morgan NAND function. And then the various packaging we can get it in. And then they, of course, give us a picture. Not much of a picture because we already know what it looks like. Of course, they're telling us, oh, we could use this in a home theater system. Well, I'm not so sure that it would be very useful in that. But they're trying to sell these things. And if you were making one of these sheets and needed to put some applications here, you'd list everything you could think of that might push your product. Now, table of contents, there's a lot of stuff in here. Knowing what to look at is fairly important. This is a picture of the pins. Notice here's one that has a little circle instead of a notch. And here's what the particular pins have. 1 through 7, 8 through 14. Now, interestingly enough, with these guys, we are going to actually look mostly like this particular package because we know we have VCC, or I'm sorry, ground down on the bottom left corner, and we have VCC on the top right. If you look at the other ones, this is close, but it's only 8 pins. And we also can look at the packaging. This guy is in a CFP package. This guy is in all of these, a C dip, a P dip. Where's is actually a P dip, a plastic dip. There's something called a ceramic dip also, which is more expensive, but is a little less susceptible to heat because it's not going to melt as soon as plastic would. Some of the military stuff only comes this way. Then we're going to get information about what the pins do, whether they're gate inputs, outputs, whatever they happen to be. And then finally we get to some absolute maximums. We have different types of chips, but the one we have is, it says that the absolute input voltage to put on an input pin should not exceed 5.5 volts. We would want to remember that. The VCC pin should never exceed 7 volts. So these are the inputs to the gates. This is VCC. So there are some absolute limits. The chip itself should never exceed 150 degrees Celsius. Now boiling is 100, so that's pretty hot. But if you boxed one of these up, or you use it in something like a car, where it can sit outside and cook itself, the chip is probably not suitable. You'd probably need to find some automotive grade pieces of equipment. That's even better than military sometimes. Automotive programming and chip building is really difficult to get it right because of all the noise and all the heat and problems. We can't store the device any lower than minus 65 degrees Celsius or any higher than the 150, which we could make the die be susceptible to. The other thing that happens is if you get it too hot, the way the chip actually is built, we don't have that picture up anymore, is the actual piece of silicon is very small and it's right in the center of the chip. Then there's little gold wires that are soldered to them that go out to each pin. Looks kind of like a spider inside. But those little solder joints, if they get hot enough, will melt and the gold wire will break. The same thing happens if you throw the chip against the wall. You abuse it somehow. You can break the little gold wire. Normally, the electrical thing, which will melt the solder as well, doesn't burn up the silicon. It burns up the wire. And so when we burn up a chip, normally we damage a chip, we've broken a pin or we've broken that gold wire through stressing it too hard. We find out the chip won't work anymore. So we need to keep some of these in. And there's also some electrostatic ratings, but only for the LS chip. We don't have any numbers for us, so we would use common sense there. Now, operating conditions are things we actually have to pay attention to in a minute. We'll go through those. The one that's really important here for us is, while those were maximums, in practice, if we're a commercial chip, we want to operate normally with our voltage at 5 volts, not letting it drop lower than 475, not higher than 525. And we'll talk about the other values in just a second. We have some other, this is if you were actually really worrying about the wattage information and each junction on board, its relationship to another junction as degrees Celsius per watt. And this would be useful if you're designing a system that's going to be closed without, it also tells you whether you need to have some sort of air cooling or liquid cooling built into your device. And finally, some more electrical characteristics, and we'll go over which ones of these we need to care about. They're a little hard to point out on the screens, but these are divided up per device. Since we're using this SN7400, we'll worry about these numbers. I will give you this data sheet as well, more than likely. If not, it was easy to find. Now, eventually down here, we get into some graphs that display the table data we saw above, and we also get into some timing information. We will come back to this during the next class. Okay, so what I want to do now is I want to actually give you some of those minimum and maximum values that are in the data sheet. Now, in doing these, you may also see some of the competing technologies. You might find a Nand Gate, which is CMOS technology. That's complementary metal oxide semiconductor. Complementary, not in the sense of, hey, I like those shoes, but complementary in the sense of yin versus yang. They're complements of each other. Metal oxide semiconductor uses what are called MOSFETs. MOSFETs are metal oxide semiconductor field effect transistors. Again, you can look these words up. Field effect transistor is not what we've been using. We've been using the junction transistors. And bipolar, I couldn't think of bipolar there for a second. Bipolar junction transistors, which the specific one we've been using is an NPN, which has 2 diodes, an NP one and a PN one packaged together, and this makes a current amplifying device. An FET, field effect transistor, is a voltage amplifying device. So they do different things, but they could both be made to implement a NAND gate. So let's talk about some of the electrical characteristics of this bad boy. And again, you should be really excited about this. I mean, this is like, who'd have thought, you know, when you were a child that you would someday get to be privy to this information. Let's talk about the voltages on the input, in particular when the voltage is high. Now I'm going to give 3 columns here. First column is going to be minimum. Second column is going to be nominal. Next column is going to be maximum. Now, what this says is the minimum voltage that will be recognized as being high on an input is 2 volts. That means any voltage from 2 to 5 volts that's on an input will be recognized as being a 1. Now, what are the voltages that would be recognized as a low? Well, that's got to be a maximum value. And the worst it will be is 0.8 volts. So that says anything 0.8 volts or less is a 0 in Boolean logic. Anything 2 volts or higher is recognized as being a 1. What do you think happens between 0.8 and 2 volts if I were to give it 1 volt? Anybody want to take a guess?
A voltage drop, maybe?
Well, do you think it's going to be recognized, if I gave 1 volt, is it going to be recognized as true or false? Is it going to look like a 0 or is it going to look like a 1? Mr. Brood, what do you think?
A 0.
Okay, that's one option. The other option is 1, right? There's a third option. It won't know what the answer is. So we always have to make sure that if we produce an input, we are creating a voltage that's 2 volts or higher if we want it to be a 1, and we have to guarantee that it's 0.8 or lower if we want it to be a 0. Otherwise, it's all bets off on what the chip will think it is. It could think it's a 1, it could think it's a 0. It could alternate real quick between those two values because it's confused. So it's up to us when we put a voltage on the inputs to ensure that it's less than 0.8 if we want a 0, and it's 2 or greater if we want it to be a 1. Okay, interesting fact to know. On the outputs, the chip guarantees us that if it is producing a high output, it will be able to sync into itself. I'm sorry, source. I wrote the wrong, I'm reading the wrong half of my paper here. Source into itself 400 microamps. The minus sign means it's into the chip, which is the clue that it's a source. So that says that if I put a 1 on an output, it's current we're measuring. If I care about the output and the output has a 1 on it, the chip can handle 400 microamps going into it. If you try to put 500 in, that's too much. You could put less, but you can put up to maximum of 400 microamps externally into the chip if it's trying to produce a 1. Now, if it's trying to produce a low, the maximum that you can sink into the chip is 16 milliamps. So clearly, this thing likes zeros better than it likes 1s. The chip can have current flowing into it up to 16 milliamps on an output if it's low. If the output is high, it can only provide 400 microamps out of the chip. We're sourcing it out of the chip, sinking it into the chip. I said that wrong the first time, so make sure you paid attention to that. Okay, so what good does that? Nothing went in the nominal column. Well, what would really go out of the data sheet in the nominal column is VCC. We said that for the type of chip we're using, 4.75 is a minimum. 5 volts is the nominal voltage, and the maximum was 5.25. All of these are in volts. So let's look now at the other possible things that could go on here. If I am one of these chips and I'm producing a high on an output, actually, let me write my labels again here. Actually, you know, the easy way to do that would be cut that line, wouldn't it? Paste it in again. So V, output high. I'm the chip. I'm going to produce a high. the minimum I'm going to produce is 2.4 volts. This no longer is a nominal at this point. This is a typical. And typically, instead of 2.4, my output, my 1, is really going to look more like 3.4 volts. It's not going to be a full 5 volts. And there is no maximum. I might go all the way up to 5 volts. But I could go as low as 2.4 volts on an output, and I would be producing a 1. Now, if I'm producing a low, there's no minimum, but the maximum value I could produce is 0.4 volts with a typical voltage on an output of 0.2 volts. Now this is interesting because this is the chip producing something. It can produce only down to 2.4 volts. But if it's another chip of the same type, its input could recognize all the way down to 2 volts, meaning that we're safe by 0.4 volts. We're producing a value that's higher by 0.4 volts than would be necessary to still be recognized. Notice that on the other end, if we're producing a low, the chip says it'll recognize all the way up to 0.8, but we're going to produce 0.4 and below. The difference between 0.4 and 0.8, or 2.4 and 2 volts, is 0.4 volts. And 0.4 volts on this particular chip, well, is called the noise margin. So I'm a chip and I'm producing 2.4, but there's some noise, so this number is jumping up and down a little bit. This could vary as far as all the way down to 2 volts and still be recognized by another chip as an input. Since typically we're operating at 3.4, that's not a problem. On the other end, since we're typically producing 0.2, but we could produce as bad as 0.4, we could bounce up and down 0.4 and still not hit the 0.8 requirement within the noise margin. So as long as our noise here is less than 0.4 volts, our outputs are compatible with our inputs. Similarly, the currents. We have I, the current, when the input is high. The maximum current that we're going to sink into the chip is going to be 40 microamps. Put that against it. The current we're going to do if the output is, if the input is low, is going to be 1.6 milliamps. So that means that if I'm producing some output and I can produce 16 milliamps out of my chip, and this guy would be negative because he's into the chip. Oops. We would actually consider down here this guy to be the sink because he's into the chip, and this guy to be the source because he's out of the chip. This number here is completely compatible with this number because it's 10 times smaller. So a chip itself can produce only 1/10 of what a chip is able to sink. Same thing with its sink on an input. It can source on the output only enough to take 1/10 of what it can sink. So we're completely compatible. The 10 that we're seeing there means our chip has something called a fan out of 10. That means I can take one chip you can feed 10 other chips with one output. That becomes a limit. If I try to do 11, I have to come up with another way, maybe feed an intermediate chip, a buffer or something, to be able to feed more. But you should keep this chart around as a way to know what the values are within a particular chip. Now, if we used a different family of chips, or the technology was different, like an LS chip, all these numbers would change. And we'd find that the output, maybe the fan out is more. Maybe it's 100 chips could be attached to one chip because somehow the values are that much smaller. Okay, let's move on. We got a little ground to cover before we're done for the night. You have this recorded. You also have thought about what those may mean. And I'll ask you some questions about that sometime in the very near future. Let me see, what's the next thing I wanted to do? Oh, yeah. Let's think about if we were building, not using TTL, but just a transistor, how would we go about hooking it up in such a way that it could act as an inverter? Remember, a transistor is using current as its main thing to be amplified, but we're putting it in saturation. So let's look at this little setup here and see if we can understand how a transistor might be used to cause an inversion to occur. Remember, we want the inversion to be in voltage, but we don't amplify voltage. We amplify current. And to do that, what we're going to do is take a little chunk and cut it out of our LED circuit. Here's the emitter, here's the base, here is the collector. We're going to put our input in over here, and we're going to only have one of two values, 0 or +5. Now, in this example, we're not pretending like we're TTL, so we can leave it at +5 as a good estimate. The base current that flows here times beta needs to be bigger than the current flowing here. Notice that these resistors are 10 times each other. So we're guaranteed that if you took this value's current and you divided it by 10, you'd get the current flowing through here. So we're going to say that the beta has to be much, much greater than 10, so that we're guaranteed that whatever current is flowing here forces this current into a saturated situation. The transistor gets turned hard on if this is got any current. So let's first of all take and assume that the value coming in here is 0 volts. Without worrying about what the current is, we know the current flows through here. We know that if there's 0 volts here and there's 0 volts here, there isn't going to be any current. So since there's no current, that means the resistor doesn't drop or raise the voltage in any way. That means there would be 0 volts here. Ryan, what voltage would I expect to see here if the transistor is in saturation? Knock, knock, McFly, you in there? Ryan, you got the answer to that? Kyle?
I do not.
What do you say?
I do not.
Anybody want to take a shot at it?
This is 0.
0.7.
Yeah, if we were in saturation, this would be 0.7 volts. That isn't 0.7 or higher or anything other value, so we know this is 0 volts. If this is 0 volts, that means the transistor is off. No current is flowing through here, so the only current in the circuit is going that way. But what we do know is that assuming this has a value out here that's not causing the voltage to change, this 5 volts is going to be seen here. So if I put 0 volts in and I get 5 volts out, that's the same as if I put a 0 in and I got 1 out. So that's step 1 of our truth table, right? We got A, we got Y. The inverter says 0, 1. We did a 0 in, we got a 1 out. If we put a 1 in, we want to see a 0 come out. Okay, let's see if I can do this. What do you think? Think that's going to work? Oh, that won't work. Let's, if I can control Z back enough to get rid of it. And instead of 0 volts, we'll put 5 volts there. Oops, use a pencil though. So we got 5 volts there. If we have current flowing through here, is 5 volts enough to give away 0.7 to this? Give me a green light if you think it is. Yeah, we got enough. We got a place for current to flow. This will turn this transistor on with a 0.7 volts here. Now, some amount of current. We know it's enough to saturate the transistor. Transistor is full on. So what value would we expect if we were designing here to see across the transistor if it's in full saturation? Oscar?
I'm not sure.
That seems to be a popular answer tonight. Gabriel? Okay. Ryan? How about you, Robert?
Sorry, can you repeat the question?
What voltage do we expect to have? You must stay at the computer more often. The voltage across VCE if we're in full saturation. If you're off doing something else, you're not going to know the question when I ask it. So what's going to be the voltage here? Okay, I actually was here that night, and I know it's 0 volts. Okay, so at 0 volts, that means that we dropped from 5 volts to 0 volts. The output connected to 0 volts means that now we put a 1 in, we got a 0 out. So this truly is a circuit that does the inverter. And we're able to see that by working our way through it. Now, you can't be 6 weeks behind thinking about transistors, because it could be that we're going to see a circuit at some point that has more than one, and we have to be able to apply them. So I guess the next thing to naturally do would be, how did they implement it inside TTL? Because I think that's going to be telling to give us a good idea of how these things really are put together. Okay, now everybody should have gotten really excited. You should have gone, wow, I know now what's inside of a TTL inverter. These two transistors right here are the totem pole. One, but not both, will always be on. The other one will be off. That's just a clue as we do an analysis of this circuit. Does anybody want to do the analysis for me? No? So the Wi-Fi problems suddenly start. Okay, so what we got to do here is we have to think about what's going on in this circuit. What do we want to have happen? We want to apply a 0 here and get a 1 here. A 1 here and get a 0 there. We're going to think of zeros and ones as being 0 volts and 5 volts. So let's start rather simply. Let's apply 0 volts to the input. Now let's think about this transistor. How many transistors are actually in this circuit? 4. Here's 1, here's 2, here's 3, here's 4. There's a resistor, 4 of them. 1, 2, 3, 4. There's a diode. This is hooked to the VCC pin on the chip, pin 14. These two grounds down here are hooked to pin 7, the ground pin on the chip. There would be 4 of these entire things inside 17400 chip. They share the 5 volts and they share the grounds, but they share nothing else. Oh, actually, this is an inverter. There'd be 6 of these because you can get 6 gates inside of an inverter. It's called a hex inverter. There's no hexes going on, but since it has a single input, there could be 6. Okay, let's think through this. This is not hard. We got 5 volts through a resistor, through a base emitter junction to ground. We've seen that a million times now. Would we expect this to be turned on? Now, we're not going to worry about the values of the resistors. They might be right, they might be estimates. But if we could get current flowing through here, we have a higher voltage going to a lower voltage, and the voltage here is big enough we can give up 0.7 here, and 0.7 is what we use if we drop across a transistor. We could say that that transistor has a 0.7 volt drop across it. Therefore, this transistor is on. Does everybody see that? Because current can flow through a resistor, through the base emitter, to the ground we've put on the pin. That must be able to drop 0.7 here and have a current. Unless this thing were just huge, this transistor will be partially on, but we're going to guarantee these numbers always make it saturate or not. So the transistor is saturated. We just had the question about what voltage would we expect to find across the transistor if it's saturated. We determined it's 0 volts. If it's 0 volts relative to 0 volts, that means the voltage right here must be 0 volts. Now, if it's 0 volts here, and we want to get to 0 volts on the other side of the transistor, do we have 0.7 volts we can give up to the base emitter? I hope you answered no. Because if you did answer no, you're right. Which means this transistor right here has to be off. Now, if this transistor is off, that means no current can flow that direction. Any current coming into this other transistor would have to follow a path that did like this. But it could only do that if it went from a big voltage through a resistor, through the base emitter, and we were able to give up 0.7 volts to this, as well as go through this diode, which happens to be pointed in the right direction, and out here. Because remember, ultimately, if we have a high value here, we're sourcing current to the outside world. And in fact, all of that's true. 5 volts is high enough to give up 0.7 here and 0.7 volts here. So we're really giving up 1.4 volts away from 5. That gives us 3.6. That's close to that nominal voltage we had when you think we're also giving up a little bit to this resistor here. So if we were able to do that, we've obviously saturated this transistor, meaning this transistor right here must be on. And if it's on, that means current can actually flow through here and out as well. So we're not only relying on the little trickle of current that we had here, but the remainder of the current up to that 40 microamps we could produce can be flowing through this leg right here. And we know we can be producing about 40 microamps because it's an output. I'm sorry, I didn't mean 40, I meant 400. Because this can produce, up to 400 microamps if necessary. It also can produce up to 5 volts if necessary, if it's a 1, which it would be looking like something closer to 5 volts than to ground, because we only dropped 1.4 plus a little bit. So this would look close to 5 volts. It would look like we were producing the 400 microamps we need, which means it's on. So a 0 value here meant a 1 value here. But now we said totem pole, so we have to demonstrate not only is that on, but that this is off. Because if this isn't off, all that nice current that's coming through that diode would simply flow to ground. So what would lead us to believe that this would be off? Well, if we look over at its base, this transistor won't provide any voltage to it, so it's a ground, back to ground. Will that 0 to 0 give us enough to have a 0.7 volt drop across it? No. So we got a 0 volt drop here. Therefore, this transistor must be off. Everybody good with that? See how simple that was? There really wasn't much there going on, right? We decided whether a transistor could be saturated or not, given on the conditions of did it have the ability to receive enough current to turn it on, and if it got the current, was there enough voltage to be able to give us the 0.7 volts across the base emitter. And if it did turn on, we estimated that the value across it was 0 volts. If it didn't turn on, we estimated that it could not receive current from the collector to the emitter. So we would assume that whatever voltage was hooked to the emitter was the same voltage, that would have been there without it. But since the, in this case, for instance, isn't on, that means simply no current can flow this way. So we're not going to lose what's flowing in. Now, homework. Same circuit. What you need to demonstrate is if we put plus 5 volts here, let me do better than that. We put plus 5 here, which means a 1. We're going to get 0 volts out here, which means a 0. And the current will be flowing into and through that bottom transistor. So you need to study the other one. So if I were to give you a blank one of those and said fill in the details, you'd be able to do that. And if I gave you this one and said, okay, fill in the details, you'll be able to do that. Sounds like a great 2-question quest. It's not a test or a quiz, so it would be, one of those things where I want to see that you did it more than how you did it, more than that you get a precise answer for it. Anybody have any question about what the homework is? I'll post this as soon as I can right after class. And I'll probably post this on Blackboard, but later it'll wind up in another folder somewhere else as well. Anybody have any questions? Because I think we're pretty much running out of time tonight. Nicholas,
so what are the things we need to find again?
Seth, you can think about it. I just told you when I did it there. It should be in your notes.
All right.
Okay. Anybody else have a question? Okay, I would suggest on this one, you work with people. Don't wing it on your own unless you're absolutely sure you can. Or wing it and then make yourself available to help other people. This would be one of those opportunities to meet some of the other people in the class, as well as to demonstrate that you know how things work. You quickly will determine if somebody is just, taking advantage of you. Quickly. I mean, that just will be really obvious. Okay, then that's it for tonight. What is today? Wednesday. You got a long time to get this done. You got till Monday. So I will see you fine folk then, and have a nice weekend. I will post the slides I did tonight somewhere at the end of class, and I'll also put this in Blackboard as an assignment or an announcement or something so you can find it and get to work on it. So have a good one. Tell me good night and be gone. That we're going to see a circuit at some point that has more than one, and we have to be able to apply them. So I guess the next thing to naturally do would be, how did they implement it inside TTL? Because I think that's going to be telling to give us a good idea of how these things really are put together. Okay, now everybody should have gotten really excited. You should have gone, wow, I know now what's inside of a TTL inverter. These two transistors right here are the totem pole. One, but not both, will always be on. The other one will be off. That's just a clue as we do an analysis of this circuit. Does anybody want to do the analysis for me? No? So the Wi-Fi problems suddenly start. Okay, so what we got to do here is we have to think about what's going on in this circuit. What do we want to have happen? We want to apply a 0 here and get a 1 here. A 1 here and get a 0 there. We're going to think of zeros and ones as being 0 volts and 5 volts. So let's start rather simply. Let's apply 0 volts to the input. Now let's think about this transistor. How many transistors are actually in this circuit? 4. Here's 1, here's 2, here's 3, here's 4. There's a resistor, 4 of them. 1, 2, 3, 4. There's a diode. This is hooked to the VCC pin on the chip, pin 14. These two grounds down here are hooked to pin 7, the ground pin on the chip. There would be 4 of these entire things inside 17400 chip. They share the 5 volts and they share the grounds, but they share nothing else. Oh, actually, this is an inverter. There'd be 6 of these because you can get 6 gates inside of an inverter. It's called a hex inverter. There's no hexes going on, but since it has a single input, there could be 6. Okay, let's think through this. This is not hard. We got 5 volts through a resistor, through a base emitter junction to ground. We've seen that a million times now. Would we expect this to be turned on? Now, we're not going to worry about the values of the resistors. They might be right, they might be estimates. But if we could get current flowing through here, we have a higher voltage going to a lower voltage, and the voltage here is big enough we can give up 0.7 here, and 0.7 is what we use if we drop across a transistor. We could say that that transistor has a 0.7 volt drop across it. Therefore, this transistor is on. Does everybody see that? Because current can flow through a resistor, through the base emitter, to the ground we've put on the pin. That must be able to drop 0.7 here and have a current. Unless this thing were just huge, this transistor will be partially on, but we're going to guarantee these numbers always make it saturate or not. So the transistor is saturated. We just had the question about what voltage would we expect to find across the transistor if it's saturated. We determined it's 0 volts. If it's 0 volts relative to 0 volts, that means the voltage right here must be 0 volts. Now, if it's 0 volts here, and we want to get to 0 volts on the other side of the transistor, do we have 0.7 volts we can give up to the base emitter? I hope you answered no. Because if you did answer no, you're right. Which means this transistor right here has to be off. Now, if this transistor is off, that means no current can flow that direction. Any current coming into this other transistor would have to follow a path that did like this. But it could only do that if it went from a big voltage through a resistor, through the base emitter, and we were able to give up 0.7 volts to this, as well as go through this diode, which happens to be pointed in the right direction, and out here. Because remember, ultimately, if we have a high value here, we're sourcing current to the outside world. And in fact, all of that's true. 5 volts is high enough to give up 0.7 here and 0.7 volts here. So we're really giving up 1.4 volts away from 5. That gets us 3.6. That's close to that nominal voltage we had when you think we're also giving up a little bit to this resistor here. So if we were able to do that, we've obviously saturated this transistor, meaning this transistor right here must be on. And if it's on, that means current can actually flow through here and out as well. So we're not only relying on the little trickle of current that we had here, but the remainder of the current up to that 40 microamps we could produce can be flowing through this leg right here. And we know we can be producing about 40 microamps because it's an output. I'm sorry, I didn't mean 40, I meant 400. Because this can produce, up to 400 microamps if necessary. It also can produce up to 5 volts if necessary, if it's a 1, which it would be looking like something closer to 5 volts than to ground, because we only dropped 1.4 plus a little bit. So this would look close to 5 volts. It would look like we were producing the 400 microamps we need, which means it's on. So a 0 value here meant a 1 value here. But now we said totem pole, so we have to demonstrate not only is that on, but that this is off. Because if this isn't off, all that nice current that's coming through that diode would simply flow to ground. So what would lead us to believe that this would be off? Well, if we look over at its base, this transistor won't provide any voltage to it, so it's a ground, back to ground. Will that 0 to 0 give us enough to have a 0.7 volt drop across it? No. So we got a 0 volt drop here. Therefore, this transistor must be off. Everybody good with that? See how simple that was? There really wasn't much there going on, right? We decided whether a transistor could be saturated or not, given on the conditions of did it have the ability to receive enough current to turn it on, and if it got the current, was there enough voltage to be able to give us the 0.7 volts across the base emitter. And if it did turn on, we estimated that the value across it was 0 volts. If it didn't turn on, we estimated that it could not receive current from the collector to the emitter. So we would assume that whatever voltage was hooked to the emitter was the same voltage, that would have been there without it. But since the, in this case, for instance, isn't on, that means simply no current can flow this way. So we're not going to lose what's flowing in. Now, homework. Same circuit. What you need to demonstrate is if we put plus 5 volts here, let me do better than that. We put plus 5 here, which means a 1. We're going to get 0 volts out here, which means a 0. And the current will be flowing into and through that bottom transistor. So you need to study the other one. So if I were to give you a blank one of those and said fill in the details, you'd be able to do that. And if I gave you this one and said, okay, fill in the details, you'll be able to do that. Sounds like a great 2-question quest. It's not a test or a quiz, so it would be, one of those things where I want to see that you did it more than how you did it, more than that you get a precise answer for it. Anybody have any question about what the homework is? I'll post this as soon as I can right after class. And I'll probably post this on Blackboard, but later it'll wind up in another folder somewhere else as well. Anybody have any questions? Because I think we're pretty much running out of time tonight.
Yeah, so what are the things we need to find again?
So if you can think about it, I just told you when I did it there. It should be in your notes.
All right.
Okay. Anybody else have a question? Okay, I would suggest on this one, you work with people. Don't wing it on your own unless you're absolutely sure you can. Or wing it and then make yourself available to help other people. This would be one of those opportunities to meet some of the other people in the class, as well as to demonstrate that you know how things work. You quickly will determine if somebody is just, taking advantage of you. Quickly. I mean, that just will be really obvious. Okay, then that's it for tonight. What is today? Wednesday. You got a long time to get this done. You got till Monday. So I will see you fine folk then, and have a nice weekend. I will post the slides I did tonight somewhere at the end of class, and I'll also put this in Blackboard as an assignment or an announcement or something so you can find it and get to work on it. So have a good one. Tell me good night and be gone.